this section. So far, okay, so this is important. So you basically have a couple of definitions here. Is a elastic and inelastic collision. So basically, the idea is if you have a collision where the objects stick together, then it's perfectly inelastic. So like in a previous example, there was like two cars and they were magnetic and they stuck together. So if you have a train, maybe a train car and it goes and it hits the other train car and then they're connected, then that would be a perfectly inelastic collision. Another word that you'll hear about it sometimes is plastic. It's a plastic collision. So then an elastic collision is, if not, it's an explosion. Sorry, I just read that. Now, elastic means that if, like in the one, again, that we kind of just did is the ball bounces, shoop, shoop, and it goes back to the same perfect height, and there's no loss in kinetic energy, then that's called elastic. Okay, so it's perfectly elastic. So you'll see it kind of written out here, so I'll just highlight it. But so you have, if it's somewhere in between, it's called it's an inelastic collision. If it hits to each other and it sticks to the wall, or it sticks to each other, then that's perfectly inelastic, or a plastic collision. If it bounces off, like, no, I just bounced off, it's cool, then it is a perfectly elastic collision. And I've never seen this because we don't do this in statics, because our goal as engineers is to not blow things up. But apparently if this happens, then it is an explosion. So that made me giggle. Okay, and so for these things in the middle, there's these things, I don't know if we're going to talk about it here, but it'll be called, in case you care, a coefficient of restitution. And the basically idea is whether or not it hits each other, it's like how much does it restore? And so like if it's perfectly elastic, then the coefficient of restitution is 0. And if it's perfectly elastic, the coefficient of restitution is perfectly 1. Like it 100% restores. And the only way I really keep it straight in my head is I just always think about a spitball like hitting the wall and just sticking. So there's no restitution. The spitball, once it hits the wall, it just conforms to the wall, has a coefficient of restitution of 0. It is just looks like that. Whereas if the ball bounces off the wall and it still looks like the ball and it's a perfect world, then it has completely restored, right? So restitution is from restore. So the ball has completely restored itself. It has a coefficient of restitution of 1. It's a perfectly elastic collision. Okay, these two, I think, so this would be, if they hit each other, that would be a perfectly inelastic, or mu, or I think it's actually an epsilon whenever I've seen it, but it's fine, don't worry about it. Or maybe it's an E this way or an E this way. I don't remember. Anyway, coefficient of restitution, doesn't matter what the letter is as long as you know what it means, and not even in this class. They smush together. I think this isn't too bad, and this is where they pop. Okay, so let's see. There's an Iron Man example, because, I mean, why wouldn't you have an Iron Man example? Okay, but I did want to work this one with you guys. Okay, so stoplight, a truck collides with a small car. Why are people always crashing in this class? I guess in statics we're always pulling tree stumps out of grounds with tractors. A large truck collides with a motionless small car. The truck comes to an instantaneous stop. The car slides straight ahead. Okay. And there is some kind of coefficient of friction happening on the cars, which means there is an external force. Okay, so let's see. I have a large truck that's 3,000 kilograms going at some unknown velocity. I'm going to call this truck A. I guess I could call it truck T because it's a truck. Look at me. I am so amazing. Okay, truck T. And then there's a car here and it's 1200 kg, and it is velocity of the car is 0. So this is unknown when I start. Okay, and then the truck comes to so it hits that, and then comes to an instantaneous stop, and then the car slides straight ahead and then stops after 10 meters. It does feel like we don't have enough to solve this problem, but I'm going to call this a collision. So basically, what's going to happen to C? So as soon as T and C hit each other, so I'm going to try it this way. So in the initial goingness, let's see, I've got an initial velocity or initial momentum of the truck and initial momentum of the car. And then immediately after the collision, the truck is still, and now the car is going. And so that's also a very weird assumption that the truck just instantaneously stops. There must have been we're going to pretend there was like a concrete barrier right next to the truck, but still the truck hit the car. I don't know. There's something else really weird going on. Maybe there was a spike in the road, so the tires just stopped. So afterward, the truck is not moving. I guess I can just put a 0 there. So the truck is not moving, and the car has an initial velocity. So this is before impact and then after impact. And now the friction is happening on the car. So then I'll look at that after the impact. So the friction happens to the car after the impact. So coefficient between the car's tires and the road was 0.62. Okay, before it stops after 10 meters. So I have a car. If I'd solve this doing momentum, it would be the car minus the friction over a period of time equals 0, because the car stops at the end. But I don't have force and time. I just have distance and, no, I do have force. So maybe I can figure this out. The friction between the tires and the road was 0.62. Okay, so I have to learn other stuff. So here was the car. It's sitting on the flat ground with a 1200 times 9.81. I hate it when I have to know things from other chapters to solve this problem. 11,772 newtons, and it has a normal force for the car, and then friction is stopping it. And we're assuming it's maxed out. It didn't tell us it wasn't, so we'll just say the F max is ba-dump, da-da-dump, da-da-dump, ba-da-dump. And in our case, those ba-dumps add up to, or multiply out to, I've already forgotten, 0.62. So 0.62, nope, 0.62 times that 11,772. And we'll see what that is. All right, so 72.99. Okay. All right, so on average, the velocity of the car, I can rewrite this because I don't have the function. I can just say it's the average force times the total time. So I know the average force is 72.99 times the total time. Okay, well, I have a velocity and a time. Ooh, I have a distance. Okay, so the distance, okay, I feel like there's probably a faster way to do this, but remember, in theory, I'm like on a test or something, and I don't have the solutions manual. I'm supposed to be figuring stuff out. So I also know that there's a distance of 10 meters. Am I forgetting things correctly? Or that's the opposite of what I meant to say, and am I remembering things correctly? He goes 10 meters. No, wait, that's Thor. Yes, the car stops after sliding 10 meters. Okay. So basically, if I start at VC there's some kind of a deceleration. I don't know what it is. I could do it like this. Equals 10. That does not seem very helpful. What else could I do? Well, I mean, I guess I could also do force equals mass times acceleration in the y direction, or the x direction, sorry, I can't math very well sometimes. So I could find that acceleration, or it's really going to end up being a deceleration, right? So I have negative 72.99 equals the mass, which I've already forgotten what it was. It was 1200. Thank you. Exactly what I wanted. 1200 times some unknown acceleration. So 72, that thingy, divided by 1200. So an acceleration of negative 6.08. Okay, now I feel like I have enough. Maybe. Maybe I don't need a time because I have a distance. What do I have? I have that VF squared equals V naught squared plus 2A delta S thing. Okay, remember, you're just trying to remember stuff that you know, and you're just throwing stuff at the wall and see what sticks. Okay, final velocity is 0 because the car's going to stop. The initial velocity is that thingy that I don't know. The delta, or sorry, this is the acceleration, and the delta S, the change in the S, is the 10 meters. See, there you go. See, now that's why I love that equation, is because sometimes you don't have time, but maybe we can find the time. But so it turns out we didn't actually need this. Didn't need this, need this, and we also didn't need this. But I just did it anyway because I didn't know I wasn't going to need it when I started this problem. Okay, so I've got that times that, and so I've got 121. VC squared equals 121. This will be like 11-ish. Square root of this thingy. Man, I hope this answer ends up being right. VC equals 11. Like that, right? So then that means now I can come back over here. So I have 30 VT equals 12 times that 11 thing. And 3.78. So the velocity of the truck was 3.78 meters per second when it hit the car, and then instantly came out to be 0. Is that the right answer? Well, they got 4.4, but they got 11 there, and it looks like they're just, yeah, what's the word I'm looking for? Randomly rounding, potentially. 36? Oh, because I said 36 and they said 30. Okay, so I did mess up. So it's this divided by 30. That'll do it. So I was like, clearly they're wrong. Okay, 4.4. Here we go. So see, you do everything right, and then you type it in the calculator wrong. 4.41. Okay, so there you go. I'm eventually able to get there, and I specifically didn't look at how the book was doing it because I wanted to show what it's like when you don't know how to work a problem, because, you know, the whole point of taking a class is you're not supposed to know how to do it when you get started. So we don't know how to do it. We play, we try, we see what happens. So I did end up writing some things I don't need, and then I remembered that I actually knew stuff from other chapters, which is why physics gets hard, is because you can't just, like, skip stuff and then know what's going on. But I think that's a pretty good problem. So if you can kind of follow that problem, you should be in really good shape. Everything else in this chapter is way more than you need for the purposes of Physics 1, probably. So I'm not personally going to go look at videos or do videos for this. If you want to go learn it, you know, you're certainly welcome to. You're like, absolutely, with all my free time, I'm going to go do all this. So I'm not going to make any more videos for this because I feel like if you really wanted to get into that, you'll do plenty of it in classes that specifically do that. And right now we're just trying to get you the kind of the basics, I guess.